I'd like to thank Alex for agreeing to talk on, frankly, extremely short notice. He found out about this 8 minutes ago, that he is going to give this talk now. Hopefully it will go smoothly. Alex does not have time for questions. This talk is more than 25 minutes long, so he's going to go through very, very swiftly. Please keep questions to afterwards. Collar him, he's around. Other than that, thank you very much, Alex.
Okay, well, thank you all for coming. Since you probably haven't had a description of this talk is going to be about something called property-based testing and a Python library called Hypothesis that enables us to do that. Hopefully, you all know that testing is a fairly important part of the software development process. It's a really important way to catch regressions, find bugs in our software, make sure that it's generally doing the correct thing. Without testing, we simply wouldn't be able to do our jobs. And property-based testing is an extremely powerful approach to this that can help you write software that's significantly more robust. So we're going to talk about 3 things in this session. First, what is property-based testing? Why is it important? Why should you care about it? Why is it something you should consider using? Then we're going to move on to talk about a Python library called Hypothesis, which enables us to do this sort of testing. And finally, I'm going to show you a few real-world examples of how you can actually use this in your code bases, give you something you can go away and put to use yourself. So let's start by asking, what is property-based testing? And to understand this, I think it's helpful to start by comparing it to the style of testing we usually do, which is often called examples-based testing. So in examples-based testing, we've got some code or function we want to test. And so we start by writing down some inputs. What sort of inputs might we pass to this function? Because we know exactly what we're passing into the test, we know exactly what's coming out, and so we write those down as well. Okay, starting to fill up. And finally, because we know exactly what we completely specify the inputs and the outputs, we run the test and we say, does reality match our expectations? And as long as it matches, hooray, the test has passed. So as a simple example, let's say I want to sort a list of strings. I could write down a collection of some list of strings. I write down what they sort to. And then I can write a test that goes through the test cases one by one and checks that the list really does sort to what I expect. Hopefully people are familiar with this style of testing. It's quite a common pattern. The problem is, that is not a test of sorting. What this tells us is that those 4 examples of lists sort correctly. We have no idea what my sort function does for any other input. It could return none, or an empty list, or the reversed list, or blow up the universe. The problem is it only tests the hard-coded inputs. And so we could make this coverage better. We could write more examples, but writing examples this way is actually not such a good way of writing tests. There are a couple of problems with it. First of all, it is boring. Somebody has to sit down, think of that example, write it in the code, this all takes time, nobody wants to do that, and as a result, that's why our test suites often have incomplete coverage. It's also hard to maintain. You're writing lots of brittle test cases, somebody's got to remember why that test case was correct. You've written down the output, well, why was that output correct? How did you come up with those test cases? You end up writing a lot of test code, and the more code you have, the more likely it is to have bugs. And test code is not magically immune from bugs. But the biggest problem is that it's really easy to miss edge cases. Okay, if you've forgotten to put in a test case for something, you do not know at all whether your code handles that correctly. And if you're anything like me and you write the test at the same time you write the code because you're a good developer, if you forgot to cover an edge case when you wrote the code, will you remember to test for it later? So this sort of test suite is not very good at getting comprehensive coverage. The problem basically is that writing random, unbiased examples that completely test our code is really hard. Humans are not a good source of randomness. Why don't we let computers do it instead? Computers are really good at doing repetitive, boring tasks. And that's the idea behind property-based testing. So rather than completely specifying the inputs to our test, we tell the computer what sort of inputs we would like. We describe it. Then, of course, we're going to let the computer draw random examples based on these inputs. Now, because we don't know exactly what the inputs would be, we don't know exactly what the result would be. So we have to give the computer a different way to tell if the test has passed. And so we have to describe the expected results. And these are the properties. And finally, we let the computer pick examples. And of course, it being a computer, it can do that very quickly, try hundreds of examples in a second, and it can see, can it find anything that breaks our test? Can it find any counterexamples? So let's think about how we might apply this to our example. We're sorting a list of strings. The input to this test is hopefully fairly obvious. It's a list of strings. Now we've got to think about, how do we know if the test has passed? How does the computer know if we sorted the list correctly? And we've got to ask, well, what does it mean to correctly sort a list of strings? Well, one criteria is that a sorted list is a list. It's not a tuple or a string or a float. That's wrong. Another important property is that a sorted list has the same items as the original list. If I've thrown away items or gained new items, that's not sorted the original list correctly. And finally, a sorted list is ordered. Now these are three fairly simple conditions, and we can express them in code quite concisely. This is what that looks like. And then what we're going to do is we're going to tell the computer to supply this strings argument with hundreds of examples of random lists of strings. But what this gives us now is a much stronger test than what we started with. Because there's no hiding behind edge cases, then we can't hard code a function that's going to give us the correct test results. And what we're testing here is not that 4 hard-coded examples work correctly. This is the definition of a list sort. So it gives us, if our code can pass it, we can pass in hundreds of examples, and every time this test passes, we've got a much higher degree of confidence in our code. We know our code is really behaving correctly. And if not, if it doesn't pass, the computer's going to try hundreds of examples, it's got a much higher chance of finding a bug we may not even have known existed, because it's doing this all randomly. So that is the idea of property-based testing. We're going to leave a blank in our test cases, just tell it to the computer, we want this sort of input and this sort of output, and it's going to fill in the blanks for us. So let's actually do this now. How do we come up with these random lists of data? It would be very tempting just to break out the random module and start gluing things together. That approach does get you a certain part of the way, but really it's actually, there's a much better, stronger approach, and that approach is using hypothesis. So hypothesis it's best known as a property-based testing library for Python. Really, though, I think of it actually as just being really good at generating random data, or in fact what I really call it's not quite random data, it's almost structured random data, and we'll see what that means in a minute. It's inspired by a Haskell library called QuickCheck. QuickCheck was the original library for property-based testing. This is an idea that comes from the world of functional programming, but it's not functional programming specific. We can use it in lots of other languages, such as Python. It integrates with all the standard test runners, so you've not got to run some unit test, nose, PyTest. You've not got to run some special hypothesis tests on the side. It just goes straight in your main test suite. And finally, it was written by David R. McKeever. David is around at the conference today, although he doesn't know this talk is happening in this slot. If you have hard questions about the library that I can't answer, go and pester David. So let's actually look at how we would take that test and run it using a hypothesis. This is what it looks like. It's not very different. And the only thing that's changed is this decorator. I hope that's visible at the back. All I've done is added this decorator @given st.lists, st.texts to my test function, and that's all hypothesis needs to turn this into a property-based test. What that given decorator is now going to do is it's going to take what it's called a strategy. This is like a recipe for random data, and it's going to generate hundreds of examples according to that strategy. So in this case, it's going to generate hundreds of examples of lists of strings, and it's going to pass them into my test function and see if it can hit an error. And if it's an error, that's great. It's going to raise that as failure. I'll show you what it looks like in a minute. If not, it's going to try 200 examples in a fraction of a second and tell us if our function sorts them correctly. This is way more examples than we had on the previous slide, and I've only had to write one line of code to get there. But the nice thing about this is that although it's trying hundreds of examples, it only registers as one test in your test run. You're not about to get swamped with hundreds of tests. So I think why should you use hypothesis? Why should you use this given decorator? Import this bit of magic rather than just writing it with the random module yourself. So I want to show you 3 features of hypothesis that turn it into a really powerful library. The first one is this idea of what hypothesis calls a strategy. So a strategy is how we describe the random input to our test. It's telling hypothesis what sort of test cases would we like. This is a recipe for random data. Hypothesis knows strategies for all the built-in types, collections, numerics, strings, text, dates, and all that stuff. So all of that is just provided for you. You don't have to do it yourself. It's really easy to compose strategies or write your own. So we already saw we're not just creating base types. We actually compose those strategies, put them together, or even use them with classes of our own. I'm going to come on to that bit in a minute. So just to show you a few examples of these strategies, this is a Unicode text. And you can see these are not nice Unicode strings. They're not the sort of nice ASCII text that you might try in your application if you're writing a test cases yourself. It will try really weird bits. It's going to try those edge cases and find the bits of the application that you're going to test yourself. We can also compose strategies. So again, this is constructing a list of integers. And these are really big and messy integers. And hopefully your application can cope with these correctly, but I bet you're probably failing to test with them in certain cases. It tries some really horrific examples, and that's, again, really nice. That it just, in 2 lines of code, I have some really horrible test case examples. And we can even use it with our own classes. So here I've created some class, person class, it's a name tuple. I can use this build strategy to compose instances of that class. And I can even tell Hypothesis, okay, well, I want some text, but names are only ASCII characters. That's not actually the case, but it's illustrative. It's illustrating an example. I can tell it that somebody's age is between 0 and 150, that sort of thing. So I can very finely tune the data I'm getting from Hypothesis to precisely fit the tests I'm writing. So it's a really powerful and rich API for generating structured random data that goes into your tests that precisely fits your data model. So strategy is just a huge amount of code that you don't have to write yourself. And that's the first thing I really like. The second thing I want to think about is shrinking. So let's say you've seen those examples Hypothesis presents. Those examples are pretty horrible. And suppose somebody comes to you and says, aha, I found a bug in your code, and when I pass in this horrible Unicode string, your code explodes. Small examples, big messy examples like that, they're nice to find bugs in, but they're actually not so useful for debugging it once you know they're there. Smaller examples, simpler examples, small strings, small numbers, they're much easier to debug, they're much easier to assess, and it's much easier to work out, okay, I have this failing example, what's going wrong? So Hypothesis, in all of Hypothesis strategies, it knows how to make simpler examples, and this is a process called shrinking. So when it finds a failing example, what it's going to do is it's going to say, okay, I found this counter example. Let me now try and find the simplest counter example that still hits this bug. Because again, it can try lots of examples really, really quickly. Why don't we let it do that and find those small examples for us, rather than it just spitting out a horrible example and us having to go, okay, what's the actual salient feature of this example that causes it to fail? So here's an example. This is a somewhat dubious proposition about list sorting. I'm asserting that if I combine 2 lists and sort them, it's the same as sorting the lists individually and putting them together, which we would be moderately surprised if this passes. And unsurprisingly, Hypothesis raises a failure, and it says that I tried the list containing element 1, and I tried a list containing element 0, and that failed. Okay, that's a really simple example, and it's really easy to see exactly why this example fails, and start debugging our program. And this, by the way, is what a failure looks like in Hypothesis. It just shows you that it prints this single falsifying example text right at the end of your test runner, single example that you can go, and it's single example of runnable code you can actually go away and start playing with and debugging and finding out where it goes wrong. But in fact, obviously we were very lucky if Hypothesis had just happened to stumble upon 1, 0 and guessed that would break our code, and of course it didn't actually do that. What it tried, these are some of the examples Hypothesis tried on the way down. That first example is horrible. And if somebody came to me and said, oh, your code crashes on that example, I'd say, oh, well, that's an obviously weird and obscure edge case. I don't need to worry about it. Hypothesis continues sort of shrinking it, trying smaller lists, smaller integers. In the penultimate example, it actually finds an example that doesn't cause the test to fail, but eventually it finds the minimized example, and that's the example it presents to you. So it's not just presenting a failing example, it's presenting the simplest possible example. And again, that makes it really powerful for starting to debug this, and it isn't something you just get if you're writing on your own. The final thing we want to think about, though, is flaky failures. Because we're generating random data for our tests here. Now, what if we have a really rare bug? By default, Hypothesis is going to try 200 examples per test run, but it's easy to imagine a bug that occurs in less than 200 is rarer than 1 in 200 cases. And if we're drawing truly random data, well, on some tests we'll find that bug, and on other tests we won't. And that leads to flaky tests, and flaky tests are really bad. You don't want flaky tests because they just add noise to your test runner. If a test is consistently failing, you know that something is wrong. If a test fails intermittently, we'll fix that next week. So we would really like these tests to be sort of, once a test fails, for it to be consistent. And so Hypothesis has something called an examples database. So when it finds a failing example, it saves that example to disk. And then the next time it wakes up and it runs that test again, it's going to look in the database and say, hey, do I have any interesting examples of examples that failed before? If so, let me try those again. And that means that once Hypothesis found a bug, it is going to keep failing that bug again and again and again until you either fix the bug, which is obviously the desired outcome, or you tell Hypothesis that it was a bad example. this is really important. This is really important. This turns this from something that's sort of an interesting science experiment into something you could actually put into a production continuous integration suite, because you can rely, you know that it's going to fail reliably. This is actually an example from production code that maybe I wrote and possibly left around. The bug is obviously this line here. So this function is going to tell me somebody's next birthday, and this genius line is how I take the computer year forward. And think about what will happen if I run that on the 29th of February. So, and I didn't spot this until the 29th of February this year. I'm embarrassed, but hey. Anyway, so I ran this test with hypothesis, and so I ran this test twice, 50 times. The first time, I blew away the cache every time. I didn't let hypothesis save any examples, and we get some really intermittent failures, like it fails 6 times out of 50. That's not very good. Like that's the sort of noise that could easily be dismissed in a test run. You think it's something else, you think it's something flaky. There's probably not a bug in your code, and when you tried to go and rerun it again, you couldn't see it. Well, it's probably fine. On the right is the test when I ran it without any caching. Now, of course, 29th of February is a fairly rare date. It's about 1 in 1,000 days, so we're not surprised that hypothesis doesn't find it the first time it tries 200 dates. But as soon as it finds that bug after 10 runs, it then fails again and again and again and again. And that shows up as a big red flag in your test suite that says, you have written some silly code, go and fix it. And once we found that bug and fixed it, of course, we can also, it's very easy to use this example decorator on hypothesis. It lets us then make sure we're going to always hit that example again. It's always going to test it in addition to the random examples. So that's the hypothesis library. Several nice features. We've got the strategies, a really rich way to generate data, to generate examples for our test without writing a lot of boilerplate code ourselves. We've got shrinking, so that when hypothesis finds a counterexample, it's not just going to show us some messy example, it's going to find the smallest possible example it can, make our lives really easy when debugging. And finally, we've got the examples database, so that when it finds a failure, it's going to fail that test consistently and reproducibly, forcing us to go and fix the bug. That's just a small fraction of what hypothesis can do. It's a really powerful library. Would encourage you to check it out, and go and play with it. So finally, I want to talk about some practical examples. I often show this to people and say, "Oh, that sounds really exciting. That's really great. I have no idea how to use it." And property-based testing does require you to do more thinking than a conventional test. You can't just rely on the hard-coded outputs. You have to think about, well, what does correctness mean for my code? And often that requires, a bit of high-level thinking. Going back to the specification, how do we know if this function is working correctly? I obviously don't know what code you're all writing. It's probably all very different, so I can't tell you what your code should be doing correctly. But I can suggest a few common test patterns that are quite helpful. The first one is fuzzing with random inputs. So I'm going to claim that it is true of everybody's code in this room and everybody at this conference that your code shouldn't crash. And that if I can cause your code to crash, you would consider that to be a bug. So we just use hypothesis, pass in random inputs, and check that the code doesn't crash. Or that if it does crash, it crashes with a series of, maybe your code will throw in a couple of very well-defined exceptions, but you should know what they are. It forces you to think carefully, what inputs am I actually allowing, and do I actually handle all of those correctly? If you do anything with dates, Unicode text, or floating point numbers, there are almost certainly edge cases here. Hypothesis will throw at you that you probably haven't thought about before. And this is a really good way of flashing this out. And it's a great thing. Every time I run this on a legacy code base, bugs fall out like they're going out of fashion. It's a really powerful test pattern. And you can start extending this, start building on this, think about making very simple assertions about the output. Can your function return none? If not, make an assertion to that effect. Does your function always return a consistent type? If so, make a written assert to that effect. Does your function always return a value within particular bounds? Make an assertion to that effect. And just try that for all of the possible inputs. This is a really fun one to get started with. A second one that's very powerful is inverses, or what I call round trip. So if you've got a function, and that function has an inverse, then if I apply the function and then its inverse, I should get back to where I started. So this is good for decoding, encoding, things like serialization logic. This particular example here, I'm generating a random date. I cast that date to an ISO 9001 compliant string, and then I use the Python date util module to unpack that string and get back to an original date. and I'm asserting that the data that after I convert it to a string and unpacking again, I get back to the data I started with. This is an example I wrote on Tuesday as just like, I want a simple example of this talk. The annoying thing about hypothesis is that it went and found a bug. And I then had to spend half an hour writing up a bug. It was I have such hard problems. But again, that's a really powerful test plan, and then there's an example of a bug it actually found in the wild. You can go and look up that issue. It's on GitHub. They haven't fixed it yet, unfortunately, but that's another really powerful application of this pattern. Another fun one is a test oracle. So I said at the beginning, we're passing random inputs, so we don't know what the outputs should be. But if we had a second implementation of our code, we know exactly what the output should be. We've got a reference implementation. And that's the idea of the test oracle pattern. If you've got an alternative implementation of the code you're trying to test, you can run them both with the same inputs, compare the output, and check, do they actually match? So this is really good if you're doing things like refactoring or optimizing code. I've been cleaning up a lot of legacy Python code at work recently, and it's really nice to be able to point the two implementations together and say, I assert that you should always match on all inputs. It's also really good, it's also good if you've got, for example, if you're writing some sort of optimization, if you've got a much simpler but slower implementation, this implementation is probably correct. Again, it's a really nice way to sort of find mismatches in logic and make sure that what you've written now really does match what you were starting with. So that's the test oracle. Final pattern I want to show you, which is this is a more advanced feature of hypothesis, but this is much more powerful, is stateful testing. So all the examples we've looked at so far have been one-off functions. I fire in some input, I get out some output, I make some assertions about the output or the side effects of that function. But of course, most of us do not just write single functions that are called once and never used again. We're writing stateful applications. So let's say, for example, I'm writing a database layer. A database might have several operations. It has, probably has some reads, probably has some writes, maybe some sort of consistency check. And I might do a unit test that checks, does an individual read work, does an individual write work, does an individual check work. But how do I know that there's not some sequence of operations that causes my database to get into a really bad way? This is what we might often call integration testing. How do we test a stateful program like this that has these many interactions? Well, I could just write a test scenario myself. I could write an integration test that hard codes. I'm going to do a read, and then a write, and then two reads, and then another write, and then another write, and then a read. But that gets us back to the problem we started with, which is that we're hard coding our test scenarios. We're telling it exactly what sequence of stateful actions it should take. So instead, we can turn to hypothesis, and we can describe the possible actions. We can tell hypothesis, how do you know if the action succeeded? And then the hypothesis can go away and try a bunch of actions like a sort of a random monkey. Try a bunch of different actions, see what works, see if it can break something, and then present you the results. So this is, I apologize, the text on the side is probably quite small, but the way you set up these tests, there's more examples on the hypothesis website. You define this rule-based state machine, and then we define methods on this class, which are decorated with the rule decorator. And this is just telling hypothesis, this is an action you could take. This is something you could do on this test. We've also got, and so in this case, I've just got a simple priority queue I can push or pop from the queue. And then hypothesis is going to go away, and it's going to try a series of the actions in different ways and see if it can hit the assertion I'm making in the pop action, which is that when I pop an item from the queue, I get the item with the highest priority. So, we would go and run this test, and then at some point, hypothesis, hopefully, if there's a bug, either hypothesis tells us it works, or if hypothesis finds a bug, we get a traceback that looks like this. This is just an assertion. It went to pop an item from the queue, and it got a different item than it expected. This is the sort of exception you would see if you hit this bug in production. Okay? You just get a random assertion that came from somewhere in your code base that says, oh, I hit a bug. You don't know what sequence of actions were taken up to that point. You don't know what state the system was in when it fell over. Now, if you're good, you might have some logging that tells you exactly what transactions were taking place, but depending on how sensitive the information in your database is, you may not necessarily know what that is. And even if you do, you might have thousands of transactions, and one of those caused it to fall over, but you don't know which one. But the nice thing about hypothesis, of course, is hypothesis chose the actions it took, so it can tell us exactly what it tried to do there, to get there. And this is the output it gives us. It's a really nice, simple output. This is a minimal example telling us, I did these exact sequence of actions, and I got a bug. That's a really powerful tool to go away and start debugging with. You've got a runnable program you can try that reproduces an error for you. compared to trying to debug this sort of stateful application based on some snippets of logs you might have from the field, this is a really powerful test pattern to have, and a really powerful result to have when it fails. This is definitely the more advanced end of what hypothesis can do, but I think it's a really powerful test pattern. I use it all the time now, and it's, I end up saving a lot of test code by doing that. So, those are a few test patterns that you can go away and get started. Obviously, this isn't all you can do. Just to give you some ideas. Fuzz your code with random inputs. See if you can cause it to crash. Do your inverses and round trips. Check data can goes around a circle. Test oracles are good if you've got an alternative implementation, and stateful testing as it takes this even further. So we've looked at property-based testing, showed you the hypothesis library, and some test patterns for practical use. Really powerful approach for testing that you can use to make your code much more robust. You can go away and start using this today. All available, all really good stuff, and I really would encourage you to do that. If you want to learn more, the slides are not online yet because I wasn't expecting to do this today. But there is hypothesis documentation, which is really good, really thorough, not just about the library, but about this style of testing in general. And David is doing a workshop on Monday about hypothesis if you're sticking around for that. So that's going to be a really good chance to get some practical, hands-on experience with this library. So, property-based testing. An incredibly powerful, thorough way to really test your code and make it more robust. I hope you found this interesting. Hope you've got something you can go away and put into practice. And on that note, I think I'm out of time. Thank you all for coming.